So distances. Distances is actually basically how far are we from each other, like how far one can go from here to there. And distances at the end is pretty much how graph theory started. And graph theory didn't start in 1999, as some people believe. Graph theory started a little bit earlier. And the reason why graph theory started is that people were bored. That is the truth. People were bored in Königsberg, which nowadays is called Kaliningrad. And Königsberg was built basically with a river, and there was an island there, and then there were some districts. It was a northern district, there was southern district, there was the island, and then there was the eastern district of the city. So I don't know how life was there at the time, but I suspect that it must have been a little bit boring, because apparently the pastime that the people had there was, can we wander around the city, take a walk from one place and visit every part of the city, but without crossing the bridges that were necessarily connecting the districts, because it's around a river, there is an island, without crossing each bridge more than once. Now, another interesting thing, by the way, is the island was called Kneiphof, which I don't really know what the deal is there, but Kneipe in German means like a pub, but not really a pub, a bar. It's kind of like, a shady bar, kind of like where you go, you only pay by cash, you know what you get there, we'll drink something, but you don't know what you will drink. Hof is like a place. So the island was pretty much called like the place of the bed bars. So you can imagine people were taking walks, they were, going, wanted to end up in the bar at the end and get drunk, they get to the bridges again. How many bridges have we walked? I don't know. I forgot. Was it one bridge, two bridges? Did we cross this bridge once, twice, or not? So they asked Euler, and graph theory was born. But in all this, we're talking about walking. So we're talking about distances, because how far we can go from here to there, how far it is from the Kneiphof to the eastern district to the northern district, at the end, these are distances. Whether you consider each link to be the same as every other link, in which case you can say everyone is one, or you do weighted links with the distance that you're covering, these are distances. So distance is really like a very fundamental concept in graph theory. But here we are seeing what happens with higher order networks, which means we are seeing what happens with hypergraphs. And so we need to define how to measure distance when you have a hypergraph, when you have an edge that contains more than one vertex at the same time, so more than two vertices at the same time. So you have typically two main ways that have been tried to extend the concept of distance. Remember, I said at the very first lecture, those who were here also last week, that many concepts extend very straightforwardly from graphs to hypergraphs. Distance is, in a sense, is one of them. Because all you can do if you want to extend distance, say, well, you do it exactly the same as with the graphs. I can go from one vertex to the other if they share, if at least two of the hyperedges in which they are overlap. So there is an overlap, I jump from this vertex here to another one, and to another one, and to another one. And then I just count the number of jumps that I'm doing, and that's the distance from the beginning to the end in my hypergraph. That's the simplest way you can do it. And in fact, that is like the traditional way to define distances in hypergraphs. That's not the only one, of course. In fact, that's why we're talking this today. Because if you just think like literally just a split second, you will realize that there is one thing here that is missing in what I just said. But let me first point out that the other one that people sometimes do is click projection. Remember the pi2 click projection. So you say, okay, fine, we do the click projection there, and then we just measure, since we end up with a traditional graph, we measure the distance from the initial node to the final node, and that's our distance. So these are two very simple ways of doing it. However, these two ways have kind of like, both of them have a little bit of a drawback. The first one, yeah, it's a hypergraph measure. But if you think about it, you're neglecting the size of the edges. Now, if we're saying the higher order interactions are important, it means that the fact that maybe a hyperedge has 3 nodes and another hyperedge has 10 nodes is something that you need to account for, you need to consider. The two shouldn't be treated the same way. And the first approach, the simple straightforward generalization, just misses that. So you don't consider that. The second one Well, the second one, you're missing entirely the higher order information, because you are projecting your graph onto, sorry, your hypergraph onto a graph. So you literally lose your higher order information, kind of defeat the purpose of what you want to do. So, well, so we need to do something here. What we want to do is we want to define a measure that will obey certain ideas. By the way, the whole situation becomes even more complicated, incidentally, for the weighted case. Right, I said before, you can have every edge that has the same size, the same length, the same strength. So it's the unweighted graph. But you can also assign weights to the hyper edges as you assign weights to the edges. And this actually complicates the matters. And it complicates the matters even more if the weights that you are assigning to the hyper edges are something that is kind of like an informational kind of weight. So it's not something that relates directly to a geometric distance, but relates to some other type of information. Could be, say, a more abstract closeness of topics, for instance, if you're building a network of scientific papers, right? In that case, if you think about it, the weight will be the inverse of the distance rather than the direct distance. So you need to account also for these other things if you want to extend the measure to the weighted case. So the ideas that we want to have here, we want to build a measure that has basically two general broad ideas. The first one is you need to account for the size of the edge. So if the size of the edges that are overlapping, and we do the jumping as we said before, is bigger, then the resulting distance between two nodes should also be bigger. Because, you know, one thing is like, imagine if you have just a 2x2 edge, they're very, very close. But if you have a giant edge that has 100 nodes, and you say, well, we're all together, so you can still consider a jump from one to the other, but this kind of like makes it more difficult, so to speak. It's like you are in a bigger space that you need to traverse. So we want to capture this intuition in the measure. The second one is related to the overlap. If you have two big edges, let's say 5 nodes here, 5 nodes there, and they overlap on one single node, then the distance from one node here and one node there should be greater, should be bigger than if instead the two edges overlap on practically every node except one. So if you have an almost complete overlap, you are basically already there. If you have an overlap on just one node and you have many, many nodes here, many, many nodes there, again, it's like you need to cross a bigger space. So these are the two big ideas that we want to capture. So how do we do this? We do it in 2 steps. We start from the unweighted case, and then we generalize it to the weighted one. The reason is actually simple, is that the generalization is very, very easy, and the things are more easily written in the unweighted case. So there isn't really here a special thing that is going to happen, when passing from the unweighted to the weighted case. It's just that writing it in the unweighted case is easier. And then the generalization, I'll show you, is very straightforward. And we are doing this by capturing this information by means of the line graph. So you remember, again, for those who have been here last week, the line graph of a hypergraph is a graph in which every vertex corresponds to one of the original edges of the hypergraph. And you have an edge whether there is, if and only if there is an overlap in the edges that correspond to the vertices that you are considering in the line graph. However, we are going to make this line graph not just a simple graph, but we're going to make it weighted and, in the general case, with loops. And in fact, this here is the formula that we are going to use for the weights of the line graph. So you can see, if the size of the edges is bigger, then this whole thing is bigger, like we said before. If the overlap is bigger, then this term will become smaller, as we said before. So this captures those two ideas that we said, that formula over there. And I'll just keep it in mind, but I'll put it back on, and then having that formula, we will define the distance between two nodes in the original hypergraph like this. So if the two nodes are the same, you are already there, distance is 0, that's fine, nothing to be done. If they're different, this is the formula here. Now, forget about the formula there, all this formalism. What does it mean there? It means that if you take these two nodes, say I and j, A and B, whatever you want to call it, okay, they may be part of more than one hyperedge in the original hypergraph. So you consider and you look at all the hyperedges that contain the first node I, and you look at all the hyperedges that contain the node j, and this is what we call like ei or ej, the sets of all the hyperedges that contain I and that contain j. Then you see this formula here, you see the distance between the two nodes, between any two nodes that correspond to any edge that contains the first node and any edge that contains the other node in the line graph, and then you sum and subtract this thing here, but then you minimize this. So you look at all the edges that contain the first node, all the edges that contain the second node, and you see which choice of one and which choice of the other will give you the smallest number here, the smallest distance in the line graph, plus this, plus that, minus that. That's it. Yes? Yep, it's the distance in the line graph. So I said. No, it's the distance in the line graph. The line graph is a traditional graph, therefore by definition the distance in a graph is the shortest path. A distance in the line graph is a traditional distance of the graph, is the traditional distance of the graph. Right. So this is the formula, yes. Yep. Yep. No. This is the minimization happens over these elements here. These are the nodes of the line graph, but effectively these nodes of the line graph corresponds to edges of the hypergraph, right? This is this. Yeah. So that's not what is asked. That is not what he has asked. He has asked something else. The minimization happens over this. But this is the minimization of this quantity here, where this is the traditional graph distance, so we know how to take it. Yeah, this is the traditional graph distance, the traditional one, this one over here. On the line graph, that's a traditional graph. There we know how to do distances. It's just a classic one. However, this question here, these comments here actually bring us to some point that I haven't said yet, but in fact I'm going to say I believe right away. In fact, right away here. Ta-da! I put the two formula right there here. And the point is, the two ideas that I said before are not the only two things that we want. Somebody, where is he? Where is Hernan here? I don't see Hernan. As Hernan was saying, yeah, I'm saying this is all graphs, but for me the graphs are two uniform hypergraphs. It's true, graphs are two uniform hypergraphs, but this means that if we define something that should work in hypergraphs, well, this should contain the traditional distance of graphs as its own particular case, because otherwise what are we doing here? So let's see if it works. Suppose that we are in traditional graphs. Then all the size of the edges is always 2 because you have only pairwise interaction. So this is 2 plus 2 equals 4. Suppose then that we're looking at a loop where E and E tilde are the same, a loop in this line graph, right? So 2 plus 2 is 4. This is 2 plus 2 is 4. If it's a loop, it means that the overlap is on both nodes. So 4 divided by 2 is 2. 2 plus 2 plus 2 is 6. 6 divided by 2 is 3. 3 minus 3 is 0. So if we are in a situation of a traditional graph, the line graph, the resulting line graph is loopless, does not have loops. Now suppose instead that we are not looking at loops, but we're looking at, A connected to B connected to C, then we have 2 plus 2 is 4. 2 plus 2 is 4 here. The overlap is on a single node. A is connected to B, B is connected to C. So this 4 divided by 1 is 4. 4 plus 4 is 8. 8 divided by 2 is 4. 4 minus 3 is 1. So in the case of graphs, the line graph here is just a traditional line graph. It is a line graph that is unweighted and loopless. Simple, unweighted line graph. Also, 2 plus 2 minus 3 is 1. So if we are putting ourselves in the case of graphs, if we want to go from one node to the next and their neighbors, this will correspond to a loop over here, so the weight is 0. So here you get 0 because nothing is smaller than 0. If everything here is non-negative. So 0 plus all this is 1. The distance between between direct neighbors in a graph is indeed 1. Suppose instead that we have the A to B to C, then as we showed, this gives you 1. So this thing is 1, plus 1 is 2, and in fact, 1 step, 2 steps. Boom. So this thing here, our definition, contains the traditional distance in graphs as its own particular case, which is another thing that we wanted to do, as we just had a question and a comment about, so perfect timing even for the slides. But we need to show other things here. Just saying, hey, look, the formula is cool, it's cute, is not enough. One thing that we need to show is that the triangle inequality holds. Triangle inequality, it's like in traditional geometry. If you want the distance between A and B, or I and J, as I have here, and the distance J and K, the sum of these has to be greater than or equal to the direct distance from I and K. So the straight line is the shortest path between any 2 points. This is what it says over there. Okay. So let's see if it works. One thing you can notice is that, as we said from the start, this thing here becomes biggest when the overlap between the edges is on a single node, because obviously you are biggest, yes, because you are making the denominator smaller, so obviously that becomes bigger, the whole expression. So if this thing is 1, these two E and E tilde are there twice, so it means that this whole expression of the weights is maximized by 1/2 times E plus E tilde times 2 minus 3, which is the sum of the sizes of the edges minus 3. So the biggest weight in the line graph, you get it when 2 edges in the original hypergraph overlap on a single node. This is going to be important later, by the way. And you have this specific majorization expression for it, this bound, this upper bound. Now, the distances, let's say, these are the expressions we saw before. These are the same formulas we had before. Just I removed the minimum because I'm saying suppose that the edges that minimize that expression there for I and J are these ones, EI and J. For J and K are EJ prime and EK, and for I and K are EI prime and EK prime. So these are our distances. Now what we want to show is that if I do this plus this is always greater than or equal to this one over here. So what I'm going to do now is I'm actually doing the sum. I'll do the sum, shuffle a little bit the terms, and we get just this. This is literally the sum. This is these terms here, these plus these. I just moved them around a bit and I grouped them. And I did that because now I have here the sum of EJ prime minus 3. But I know that that thing there is minorized by the weight of EJ prime. So I can say that this whole thing is greater than or equal to the exact same expression, but I'm replacing this with the weight between EJ and EJ prime. So cool. Now, look here, these 3 things here. 1, 2, and 3. What are they? They are this. The distance between EI and EJ, the distance between, so the weight EJ prime is like this line over here, and then the distance between EJ prime and EK. This thing here is a representation of the line graph. But then this thing over here is just literally the length of this path going. See, this is the EI. These are all the nodes in the line graphs that correspond to the original, to the hyperhedges that contain the original node I in the hypergraph. This is the same for J, this is the same for K. So these 3 terms, the first 3 terms there, literally are this distance here plus this over there. But this is a line graph. As I argued before, this is a traditional graph, which means that if I'm taking this distance over here, I'm talking about a traditional distance, like Gandhi was asking us before. But if it's a traditional distance, it means that that traditional distance already obeys the triangle inequality because it's a traditional Euclidean, well, not really Euclidean, traditional one. So it means that these 3 paths here, this thing over there, is greater than or equal to, sorry, it's less than, greater than or equal to, then the distance between this node here and this node here. So this distance here, if I had it from EI to EK, will be certainly smaller than or equal to these three terms over there. So this means that, you know, from here, this is greater than this, I can take these three terms there and replace them directly with the distance in the line graph between EI and EK. So now I'm getting that the sum of the distances between I and J and K is greater than the distance in the line graph between EI and EK plus these three terms over here. Okay, very good. But if you remember this thing here, if I take the minimum over all the possible EI and EK, I get exactly by definition the distance between I and K for our definition. And indeed, here, if I do this, this is the minimum, it means that EI and EK, the distance in the line graph between EI and EK, since I know that is minimized by EI prime and EK prime, this thing here is itself greater than or equal to the true distance between I and K, which means I can take this whole thing here and replace it by the distance between I and K. So again, this is a chain of majorizations, analysis one, you know, kind of like these tricks that you learn there. It's just, you know, kind of a bit tricky to figure out how to move the terms around, and that's it. So the result is this: the distance between I and J plus that between J and K is greater than the distance between I and K. That's it. It means the triangle inequality holds with this definition. So, okay, cool. But this was unweighted. How do we do it for weighted hypergraphs? We do it like this. Suppose that we are assigning a weight W to the edges. That can be, it's basically a scalar field, okay? So it can be anything you want. Assign your weight W. But suppose also, for the reasons that I said before, that you may want to associate a function to that weight. So that you can say, I know the weight, but for me, I want to interpret that weight in a certain way, or I want to interpret it in a certain other way, and that will be our function F. Then we define the weights in the line graph this way. It's basically the same expression as before, but kind of like with a slight modification. I'm multiplying the function of the weight by the sizes of the edges over here, and I'm multiplying the 3 by the average of the function of the weights. F can be anything you want so long as it's positive, okay? So if you do that, you define the distance this way. Again, it's basically exactly the same. Multiply by F, multiply by F, multiply by the average. If the nodes are different, if nodes are the same, it's 0. And that's it, pretty much. So again, for the same reasons that we saw before, this definition becomes the classic definition of distance in graphs if you have all the hyperedges that are of size 2. So before saying that we are done, there's 4 things that we need to verify. The 4 properties of a metric. Property number 1, distance between a point and itself must be 0, but I wrote here that for distinct nodes is this and 0 otherwise. So by definition, that one is true. Number 2, the distance must be positive, always positive. Well, positive or 0. If the nodes are distinct, it must be positive. Everything, oops, I've lost the pointer. Everything here is positive. So obviously, the result has to be positive. So number 2 works. Yes? Yeah, probably. Where is -3? Yeah, -3. Huh? Oh, no. No, because the thing there here, if you remember, is this thing here becomes smallest when all the edges have size 2. We showed it before. So if the hyperedges are bigger and bigger, this thing becomes more and more positive. When the hyperedges have size 2, the thing is 1. So it's monotonically increasing in the hyperedge size from 1 onwards. That's you thought, non ti aspettavi chi fossi loico, as Dante was writing. And so number 2 is always positive. Number 3, we need symmetry. And again, let me get back to the formula. The formula is symmetric. If you swap E and E prime, everything is symmetric. So identity, symmetry, all these things, positivity. And number 3, is the triangle inequality. Proof of the triangle inequality is identical to what I showed you. Incidentally, just to be, for the more mathematically minded in the audience, this only works because this expression here and the one of the weights before decouple the functions of the weights of each edge with the sizes of the other edge. You don't have cross terms and correlations, otherwise the triangle inequality would not work. So we prove them all, so everything's fine. And concluding, we have finally a distance, a properly defined distance, metric distance for weighted and unweighted hypergraphs. The general one is for weighted. It reduces to unweighted if all the weights are the same. It reduces to traditional graphs if all the edges have size 2. Don't have time to show you the results over here, but we tested this on real world networks and it makes a difference with respect to, say, click projection. If you do click projection and you say what's the distance between this and that, you basically lose some information. As expected, you lose it more where the higher order interactions are more important. If you take data sets that are mostly pairwise interaction and a few 3x3, 4x4, then you don't lose much information. If you have stuff where you have a whole spectrum of sizes of interactions, then actually the differences are substantial. Mathematically, this is well defined because all the properties hold, as I showed you. And I close here. This is the founder. I need to put it, otherwise they get offended. And I'm happy to answer any questions.
Thank you a lot. Thank you a lot. So I imagine, for example, that the distance here will be very, very different for the collaboration graph, because collaboration graph, you have papers of authorship, any number of votes.
Yeah.
So there, the higher order interactions are important.
Yeah, as I said, if the set has many higher order interaction matter, this is very important. If you are basically having everything 2x2, then who cares?
So, time for questions. Please. No. We need to have
microphone, wait.
Wait.
It's on.
Bow.
Bow, meow, meow.
Let's.
Do you think that this kind of definitions could be also easily extended also to the case of directed hypergraphs or not? Are you working on...
ci penso, aspetta.
Okay.
It's not easy to answer. This is not easy to answer.
See, the problem with directed hypergraphs is that mostly you have a situation where you have a number of heads and a number of tails, as we have seen.
Yes.
So the moment that you have one head and one tail, so to speak, then it's easy. Otherwise, you need to make sure. I think that I have a feeling that the answer is yes, but I also have a feeling that there will be a problem of redundancy due to the fact that you may have more heads and more tails. So probably yes, but it needs to be done carefully. Frankly, this also here you need to do it carefully because there have been other previous attempts, and then basically you can notice that they work, but they work only for a specific case. Say they don't reduce to graph distance, or they don't reduce to unweighted, or the triangle inequality doesn't hold, or similar things. So the problem is making every single piece work together. So I believe
a good
future
project,
thing. It's a good project. I think the answer is yes, but you need to be careful. I don't know how to do it though.
Thank you.
Sure.
Thank you.
Other questions? Please.
Thank you. This is the only measure already defined by hypergraph for hypergraphs, or there?
No. As I just mentioned, what happens is that there's others. Okay. The problem with the other measures that, well, first of all, you can do the very simple one as a jump. Okay, but even if you restrict yourself to measures that consider the sizes of the hyperedges and the sizes of the overlaps, there are other measures. However, these other measures had the problem that either they did not contain the unweighted version as their particular case, or that they did not contain the traditional graph version as their particular case, or that they did not satisfy the triangle inequality. So obviously for the third case, it's not even a well-posed measure. It's like, you cannot say that that's a metric space. You're going to make a metric space with that one. In the other cases, you can say it works here, But then if you apply it to a two uniform hypergraph, so a traditional graph, you end up with a different concept of distance, which is something you don't want, and so on and so forth. So this is the first that does all this together.
Okay,
So
thank
it's
you.
the first general. And now the
General
question is, if you have now a general definition of distances, how you can generalize to hypergraphs those graph measures that are based on distances.
Well, I mean,
Fundamentally, efficiency,
closeness,
vulnerability, closeness,
between S centrality.
all
Well,
these things.
That's easy. If that's a question answer, that's easy because they depend on a distance, but they don't depend on the concept by means of which the distance
Yes,
is defined.
exactly.
So you just plug it in and it works.
Yes. So, and how long, I mean, in terms of computational effort is finding, I mean, Dijkstra. If I have a matrix, I plug the matrix, Dijkstra, tac, give me the distances. This, I have an hypergraph.
Fibonacci heaps are a very nice data structure that I did not talk about in my lecture before, but they allow you to optimize the Dijkstra's algorithm pretty well. It's basically the only reason why people study them in algorithms and data structure courses. So if you do that, you end up with a Dijkstra that you can run it in a fairly reasonable time. The problem here is that you have the minimization term over there. So the minimization term means that you need to, unfortunately, recompute other types of distances and all. You can do that at the end, not when you don't have any trick to do it more efficiently. It's still polynomial. I forgot how it is. I think it's O of nm, so n cubed. O of nm in the sparse case, or O of nm squared in the dense case. I got it written down, not with me actually, but it's still polynomial, which is actually good. Because as I argued, as I pointed out last week, in many cases when you pass from graph to hypergraph, stuff that is polynomial, even linear or sublinear, goes like to exponential. It's like, oh God. Whereas here, at least we are still in the polynomial in P space. So it may be not really a very nice polynomial, maybe particularly big exponent if you have large edges, but it's at least not exponential. I mean, even n to the fourth is better than e to the n, right? So,
other questions? If not, I don't. Okay, one. Yes. Please. Thank you.
Thank you. Is the world smaller with this? Is the world smaller with this distance?
No, the world is not smaller. It's actually as a different geometry. Yeah. I understand the question.
When do you apply it for in real world data?
Yep.
You realize that.
Yeah, I understood your question. So the answer is no. The world doesn't become smaller with this distance. It actually has a different geometry. So if you do the quick projection, you may find that two nodes are, say, close, whereas if you take into account the full information, you may realize that these two nodes are not as close as you thought. They may be further away. Or other nodes that you thought were actually far by click projection, they may end up being closer. So it's not that the world becomes smaller if you apply this, but it distorts a bit the geometry. It's a different geometry.
Okay, if there are no other questions, we thank again our speaker, Charo. And I also give